Making sense of continuous human physiological data, like chaotic EEG waves or fluctuating heart rates, requires isolating patterns inside an endless stream of noise. Ascend Aegis built its foundation by training artificial intelligence to read these complex biological signals. This flowchart outlines how that raw data is traditionally prepared in a clinical setting. Information from a sleep study is decrypted and then chopped into highly synchronized 30-second chunks called epochs, organizing the noise into a sequential format the AI can read. This recurrent neural network maps sequence analysis. Data enters the input node, merging with a hidden state, a memory of past signals. Looping this historical context into calculations lets the network predict unfolding conditions at the output node, like identifying sleep stages or extreme fatigue. In a civilian medical facility, this architecture relies on massive centralized cloud servers. The system has access to nearly unlimited bandwidth and computing power to churn through the data. But Ascend Aegis set out to take this exact clinical tool and deploy it into remote communication-denied defense operations in the Arctic. In those extreme environments, the standard cloud model collapses. A 100-millisecond delay to bounce data to a remote server and back is acceptable for a web browser. When an operator's life is at risk in a blizzard or a drone's thermal limits are peaking, a fraction of a second of latency is a fatal bottleneck. To solve this, Ascend Aegis engineered a pivot. They stripped their clinically validated AI of its reliance on the cloud, adapting it into a dual-use platform that functions entirely on its own. This relies on edge computing, the process of moving the computational heavy lifting away from remote data centers and pushing it directly onto the local field devices themselves. Hardware manufacturers have begun building specialized neural processing units directly into small, rugged electronics. These chips allow the complex RNN inference to run locally, right where the data is generated. Out in the field, this software integrates directly with hardware, like pulse-driven drones and wearable biometrics, keeping track of operator readiness and autonomous system health through heavy Arctic interference. Analyzing the data on-site eliminates the physical distance the signal has to travel. Anomaly detection and decision delays drop from hundreds of milliseconds down to single digits. It also protects fragile local networks. Instead of flooding the pipeline by transmitting massive streams of uncompressed raw telemetry, the edge device only transmits the final, vital alert. This creates an immediate data sovereignty advantage. Sensitive health biometrics and operational readouts are scrubbed, anonymized, and analyzed locally. The raw data never touches the public internet. By decentralizing the processing power, the system grants individual operators and uncrewed systems instantaneous, secure decision support without requiring a tether to the outside world. But a fleet of highly intelligent edge computing devices still faces a critical vulnerability. If the local communication grid collapses, those devices are completely blind to each other. Traditional Wi-Fi operates on a hub-and-spoke architecture. Every single peripheral device has to establish a direct line of communication with one central router. If that central hub loses power or suffers heavy interference, the entire network fails. The nodes are isolated instantly. A mesh network solves this by eliminating the central hub entirely. Every single edge device, drone, and sensor acts as an interconnected node, creating a dense, overlapping web. Internal software utilizes dynamic routing. When an alert needs to be sent, the system calculates the most efficient series of hops to bounce that data from node to node until it reaches the end user. If a node is destroyed or loses battery power in the field, the system instantly reroutes the data through the surviving nodes. The grid heals itself. Adding more nodes allows the signal to push around physical obstacles, eliminating dead zones and providing seamless roaming for drones and moving troops. The resulting architecture is deeply resilient. Deep learning biometric models process heavy data directly on edge processors and instantly share critical alerts across a self-healing communication web. Ascend Aegis took a system built for clinical healthcare diagnostics and hardened it into a made-in-Canada operational intelligence stack. It delivers secure situational awareness, no matter how remote the frontier.